Okay, welcome to class meeting 18 of the EECE574, the graduate level probability and random processes. Due to my own problem, homeworks has not been assigned for a while. So from today, homeworks will be assigned. And you need to be prepared for the second quiz. That will be probably next week. Okay. So we were supposed to have around 28 class meetings, and around at 21st class meeting, we are scheduled to take the second quiz. So before the second quiz, I will assign some homework problems so that you are better prepared. There are some corrections or clarifications on what I talked last time. So let's see the necessary and sufficient condition we derived for the mean ergodic in the mean square sense. So this was the part of the proof for a random process to be mean ergodic in the mean square sense. So here, we first defined kind of uncountably infinite number of random variables. That is a kind of time average for on a finite interval of length 2t. So by changing capital T, we can have uncountably infinite random variables. And now, since we assumed this random process has constant mean, the mean of each random variable is the same as the statistical average. So this is assumed. And now, in order to show that this random process is mean ergodic in the mean square sense, we just rely on the definition of the mean square convergence of a sequence of random variables. Since this mean of the random variable is always same as the statistical mean, which is the target value, the limit of the sequence, we subtract this target limit from a sub xt and compute the mean square. And since this target limit is same as the ensemble average of this random variable, one good thing is that what we are going to show, which to converge to 0, is nothing but the variance of this random variable. So we just compute the variance of this random variable, and we are going to show that this variance converges to 0 as capital T tends to infinity. So after simple manipulation like this, probably you remember, whenever we have something square, where we have integration with some dummy variable, we should change one of the factor to have a different integration variable. So this expectation of integral squared becomes two-dimensional integration, as you see here. And this two-dimensional integration has integration region in this T1 versus T plane, a square region. Since we also assume the random process is at least y-sense stationary, this covariance function is a function of only the time difference, which means that, as I've shown here, on each line with different intercept, y-intercept, the covariance function has the same value. By exploiting that property, we can convert that double integration into a single integration. as shown here. And so this variance is now becomes a single integration. And as I've shown, draw here, the meaning of this one is you have first the function of tau, the delay, which is the covariance function as drawn here. And you window this covariance function with a triangular function with width 4t, because the x-intercept is plus minus 2t. And you integrate over this interval. So you properly suppress the tail of the covariance function and you integrate. Here, you have to be careful in that the coefficient is 1 over 2t, not 1 over 4t. Last time I said that this is what? This is time average on a finite interval of length 4t. And some of you showed some little perplexed face because this is not 1 over 4t. But we can always interpret it as 1 over 2t as 2 over 2 times 1 over 2t, which is simply 2 times 1 over 4t. So this is nothing but twice the time average of this product on a length 4t. That's why last time I said that the Wilson stationary random process is mean ergodic in the mean square sense if and only if the triangular windowed autocovariance function has time average that converges to 0. Because the scale 2 doesn't matter. 2 times 0 is anyway 0, right? That's why I said last time this condition as triangular windowed autocovariance function when time averaged, and you want to have something like that, right? And this is time average, right? Tends to 0 as t goes to infinity. So that is a necessary and sufficient condition. And this is kind of clarified or corrected, part 1. And second one is this. Last time, from here to here, I made some confusing remarks. The first thing is this. From here, what we are going to do is that we take the absolute value of this integration to upper bound this quantity. And let me write here. So this one is upper bounded by 1 over 2t integral. Since this part is always non-negative, I can just take it. And here goes the absolute value of the covariance function, which can be, this covariance function can be positive and negative. So we take the absolute value. And now, here we need some other steps. And first thing is that we may show that this tends to 0 to show this quantity tends to 0. So it's a kind of sufficient condition. But this is too obvious. So we make another upper bound by replacing this to constant function 1. Then we have the absolute value of the autocovariance function. So we may say that the absolute value of autocovariance function has what? What is this one? When t tends to infinity, that is the time average of the absolute value of the autocovariance function. So we may say that if time average, I change it tau to t because time average without unless otherwise specified, it always function of t. So if this tends to, this is 0. Then mean ergodic in the mean square sense. So this statement would be a sufficient condition. Very simple sufficient condition. Be careful. Time average is without, unless otherwise specified, is average over t. So I have chosen t instead of tau. Got it? Even though this tau, here, tau appears. Anyway, and then we also see that one of a sufficient condition for this to hold is that the absolute value of the autocovariance function has what? Has finite integral. So another sufficient condition is that, so sufficient condition 1 and sufficient condition 2 is that if this is finite. What does that mean? If the absolute value of the autocovariance function is absolutely integrable, then what happens? This implies this condition, and this implies necessary and sufficient condition. So again, mean ergodic in the mean square sense. So we have two sufficient conditions. You may say that, okay, this is also a sufficient condition. Sorry, not this one. This one is also a sufficient condition. Yes, you are right. But usually this one and the absolute integrability is much easier to show in most of the cases. And our Peebles textbook just use the second sufficient condition. That means the autocovariance function is absolutely integrable. Got it? But last time I just said the second sufficient condition only, not the first sufficient condition. First sufficient condition is more stronger than the second sufficient condition. This is very loose condition. Or how do you say that? No, not loose. This most restrictive solution. I reversed, sorry. More restrictive. So it's like sufficient condition 2, sufficient condition 1, and necessary and sufficient condition. Got it? So if S2 is satisfied, then S1 is satisfied, and then necessary and sufficient condition is satisfied. Got it? And by using these necessary, sufficient, or sufficient conditions, we can easily show that some random process is mean ergodic in the mean square sense. So I believe that is now clarified. And same here for discrete time case. This is the necessary and sufficient condition. And there is one more, sufficient condition. And this is the kind of second sufficient condition. The covariance function is absolutely summable in this case. And also, I have another one to clarify is the mean square ergodic in the distribution function. And this ergodicity of something is always related to the time average of something and statistical average of something. So here, the something is the distribution function of the random process. And specifically here, this distribution function is the first order CDF of the random process. So where is first order CDF? Here is the first order CDF. I've deleted because it was confusing. So the distribution function is this one. And as you see here, if we properly introduce an indicator function, the statistical average of this indicator function is nothing but the first order CDF. So our statistical average of this indicator function is time average of the same indicator function. That means what? Distribution organic. And for the convergence, we are going to use the simplest mean square convergence. So here goes the same approach. The difference is that we have to consider the autocovariance function of this indicator function instead of random process. So here we have the I sub x means this autocovariance function is the autocovariance function of this random process, not the original x of t. So as you remember, when we studied from the Poisson random process, the process is a counting process which has monotonically non-decreasing sample path always, right? So it can never be stationary. If the process is not stationary, it's meaningless to show ergodicity, right? Because if you time average, for example, the mean will blow up eventually, right? However, if you convert the Poisson process that is not stationary process into, for example, a discrete time random process, especially the inter-arrival process, then what happens? We have a stationary discrete time random process. In that case, after converting the original random process to another random process, we can show that process is ergodic in some sense. Similarly, here, even though we are given x of t, to show, for example, this random process is distribution ergodic in the mean square sense, we kind of convert it to another random process. And then using the autocovariance function of this random process, we show some ergodicity. Got it? Yeah. Okay, so we have covered this part, and also we have covered this part. Got it? So last time we not only studied the distribution ergodic in the mean square sense, we also showed the mean power autocorrelation ergodic in the mean square sense. And all the necessary and sufficient conditions were involving triangular window and the autocovariance function, and time average, or sometimes absolute integrability or absolute summability of the autocovariance function. Today, we are going to eventually move to section 3 and 4 of the Peebles textbook. So, which is very closely related to the ergodicity. So here goes the correlation function. And we are going to study the properties of autocorrelation function and cross-correlation function and other correlation type functions and all their properties. Before we study the details, let's remind us one of very friendly random process given by this one. Here, even I have chosen a constant for the coefficient. Usually I have chosen capital R, which was a Rayleigh random variable, but in this case, it's even a constant A. Got it? So the random process equals A times cosine 2 pi f0t plus some random variable theta. And this random variable theta, we'd better choose a uniform on 0 to 2 pi. And here I missed, but we assume this is non-zero. Now, we already know that this random process has each sample path. That is a simple cosine function with some offset theta. So depending on the realization of theta, we have shifted version of A cosine 2 pi ft. So in one realization, we observe a cosine function with amplitude A. Now, let me ask you a question. First, what is the time average of this sample path? And you know that whatever theta we have realized, the time average of the process is 0, right? Because you integrate on some interval, there are many periods that cancels, and we have very small number uncancelled. However, if we increase the integration interval, that interval in the denominator goes to infinity, and this integral is bounded, right? Cannot be larger than some finite number. So the time average of this random process equals 0. We know that, right? And also interesting thing is that the statistical average of this random process equals 0 for all t, because theta is assumed uniform on 0 to 2 pi, right? What else do we have? Let's move to the second order case. So we may compute the autocorrelation function, which is same as the autocovariance function because mean is 0. And we already know that the autocovariance function is what? Is a function only of tau and given by this one. Okay? So it's a function only of tau. Got it? And now let me ask you another question. We've seen in the last class meeting a necessary sufficient. By the way, this is now what? The random process is wise and stationary, right? 0 mean, and autocorrelation function is a function only of time difference. Now, let's apply our necessary and sufficient condition for this random process to be mean ergodic in the mean square sense. So you still have a cosine function. Now it is exactly centered at the origin. So you have a cosine function. What do you want to do? Which condition you want to use? First, let's try whether this autocovariance function is absolutely integrable. Is it absolutely integrable? You are given cosine function. So if you take the absolute value, then this negative part flips up. And if you integrate, then that blows up. So the strongest sufficient condition we've seen does not work, right? Now, let's consider a little loose sufficient condition. What was that? We computed time average. So let's change this to t, and time average of absolute value of t. Then what do we have? So we flip and we have absolute value of cosine. And if we integrate that integral asymptotically linearly increases, right? And we divide by the interval 2t or 4t, and that will not converge to 0. So this also does not go to 0. It's not 0. So Cxx tau is not absolutely integrable. Now let's move to the necessary and sufficient condition. What do we do? Now, good thing with the necessary and sufficient condition is that we didn't have absolute value. So we can let this cosine function cancel itself by increasing the interval. And we can show somehow that the necessary and sufficient condition is satisfied. So this random process is mean ergodic in the mean square sense. And also, as you see, conceptually, given any sample path that is realized, if you take the time average, then we've seen that already its time average is 0, right? And that is same as the statistical average. So even though sufficient condition 1, 2 didn't work, the necessary and sufficient condition makes this process mean ergodic in the mean square sense. So in this sense, this example, very simple example, is a very good example. Got it? Your sufficient conditions does not work, but your necessary and sufficient condition works and shows it is mean ergodic. And we'd better remember this because this is a very special, this serves as a very special kind of counter example in what you are going to see in what follows. Okay, so this is very important. Of course, more important example is when we have capital R, which is Rayleigh, and theta uniform on 0 to 2 pi, because that process, as you've seen now, and now probably now you remember, that is what? Strictly stationary Gaussian random process, but having very special autocorrelation and autocovariance function. That is something times cosine 2 pi f0 tau. So if you delay the random process, this process and that family has very strong correlation. Whatever time shift you have, however, it is still ergodic. So in that sense, it's very interesting. When I take some statement from Stark and Wu's textbook, it said that if a random process is kind of uncorrelates as the time delay increases, then it is likely to be ergodic, right? Because if you take a segment, they kind of becomes uncorrelated. And due to the weak law of large numbers, if you take the entire time average, it may converge to statistical average. However, this provides a very special example. That statement is not always true. In most of the cases, that Stark and Wu's statement is true. And that is the good understanding of your ergodicity. However, this example is a kind of strange thing. You'd better remember. Okay, now, most of the materials are very familiar to you. First, definition of autocorrelation function. You've seen it already, right? So given a random process x of t, the notation capital R sub xx, t1 and t2 is simply ensemble average of this left side random process evaluated at left side argument times the right side random process evaluated at right side argument. Be careful. Here we assume that it's a real valued random process. So in general, we define for complex valued continuous time random process, the definition is what? Expectation of x of t1 and x conjugate t2. Because we reserved this definition for complex valued, using without conjugation and called this as pseudo autocorrelation or complementary autocorrelation function for complex valued random process. Got it? So whether a random process is real valued or complex valued, you may say this is the definition. But if x is real, this is same as that one. Okay. And most of the times, we do not just use T1 and T2, but we use T and delay or advance tau. So instead of using T1 and T2, we may write this way. But here again, we assume X is real. So we'd better have conjugation here for complex valued random process. Got it? And as I told you, one of my convention is that since right-hand side has something conjugate star, the left side has tau. That is one way to remember. Okay. Sometimes people use different definitions, but similar, like this. T minus tau. Got it? If X is real, this and that are the same, right? However, for complex valued, they are slightly different when they are not Ysen stationary. And I really prefer that one. And I kind of come to prefer this definition because if you develop your theory based on the multiple input, multiple output linear system, then this definition works much better in most of the times. That was my lesson for last 2 decades. Okay. Given the definition of the autocorrelation function, here goes a kind of extreme, a special case of this definition. And here goes the definition. A real valued continuous time random process is called second order process. But as we've already seen that, some people say it's a regular process because second order means too much, okay? When the random process has ensemble averaged instantaneous power always bounded. But for complex valued, you'd better use this definition. Okay, so you take the modulus of the random process, complex valued random process x of t and square and take the ensemble average. And in general, this is parameterized by t, right? And for every t, this ensemble averaged instantaneous power is bounded, then it's called a regular process or a second order process. And this assumption is quite often used in order to remove some strange pathological, in Korean, 병적인 situations. Because it's similar like you cannot divide by 0 in our mathematics, our human being developed, something like that, okay? Because if it is infinite, then there comes some subtleties, got it? So this is important, but in most of the times you can just ignore, especially for practical problems, because no random process practically has infinite power at any moment, right? If there exists that kind of random process, probably human beings have been exploiting that to get infinite power and infinite energy and feed our power grid. And you don't know, we have power hungry animals, right? So this is a kind of pure mathematical thing, but sometimes very important. Now let's see some statements and remarks. Suppose x of t is at least Ysen stationary. What does that mean? At least Ysen stationary. It could be strict sense stationary. It could be stationary to order million. But anyway, here, what we assume is very simple. Expected value of the random process is constant, some c. Let me use x bar because we have been using that one for all t. And the autocorrelation function is a function only of time difference, right? So as I've shown here, at least y and stationarity means that there exists a single variable function that is same as this two variable function. Be careful. I also got very confused when I first saw this one, because in the left-hand side, you have a two-dimensional function r sub xx, right? So here, this guy, according to our standard notation, to specify the domain and range of a function is what? R squared into, if this is a complex valued function, C, right? So this function has domain R squared. And this function, even though having the same name on the left-hand side, is a totally different function because it has different domain. So this equality is a very severe abuse of notation. However, everybody does that. The problem is that when you first see it, you have a lot of confusion. After several years, it's kind of breathing the air. But be careful, got it? So this simple equation means that there exists a single variable function. And we just name it the same. And that is same as the two-dimensional function of t and tau, but only on tau. Got it? So it says there is a real value. In this case, this is real because we assume x is real. And this equality holds. And here goes a kind of question. The single variable autocorrelation function can have an arbitrary shape, which means any function can serve as an autocorrelation function of a random process? That is the question. Let me repeat. Does any function, can any function serve as an autocorrelation function of a random process? Definitely the answer is no. Okay? And it is unfortunately hard to explain then what kind of function can serve as an autocorrelation function. For example, suppose this is the set of all real, let me see, in this case, since x is real, all real functions that has r into r, okay? Then there is a small subset of functions. And this, each element of this subset can serve as an autocorrelation function of a real valued y, at least y and stationary random process. Very small set. And we can not easily fully characterize this set at this moment, but we will be able to do that after we study the power spectral density. And some of you already have been exposed to the notion of power spectral density in your probably undergraduate probability and random processes. However, in this course, we haven't yet defined, and we are going to define that. Got it? So even though your undergraduate program didn't cover the topics up to power spectral density, it's okay now. Got it? So let's partially characterize this set. Okay? So here goes a kind of necessary condition. It's a necessary condition for a function to be a member of this set. Got it? And for now, we only focus on real valued real-valued random processes. For simplicity, we can not difficultly extend these properties for complex-valued random processes. Okay, first thing, in order for a real-valued function to be a member of this set, first necessary condition is that it must be an even symmetrical function of tau, which means that it must be symmetrical with respect to this vertical axis. Why? Why this is true? And whenever you have something to show, and that something involves notation, not the definition, then convert the notation into the definition. As I told you, this is a notation to say that right-hand side is an autocorrelation function of x of t, right? So let's rewrite this one. Expectation of xt plus tau and x of t, and which happens to be not a function of tau, right? Because we already assume it's at least wise and stationary. And what is the left-hand side then? But in order to do that, let's use the commutativity, which means in Korean, 교환법칙, commutativity of the multiplication of two real numbers. As you know, 5 times 3 equals 3 times 5, same. So what we do is that we change the order inside this ensemble average, and we can write it here. Now, see the relation between this notation and that definition. Here, tau is nothing but the left argument minus right argument. So what does that mean? If we apply this notation, then this same quantity is what? R sub xx t, which is left argument, minus t plus tau, which is the right argument. Then what is this? R sub xx of negative tau. That's why we have the even symmetry. So first necessary condition for real-valued function to be a possible autocorrelation function is the even symmetry. Second one, so this is kind of a necessary condition 2. When we have a regular process, the function is bounded. What does that mean? The function is bounded means that if you take the absolute value or modulus, if it is a complex value, and you draw in your mind the graph of that absolute value of modulus. And then you can find a finite number. And for all time, or in this case, for all t, this absolute value is less than that finite number. Then we say that the function is bounded. And here, the second necessary condition says that the function, for a function to be an autocorrelation function over at least wise and stationary real-valued random process, is that it is bounded, and that bound can be chosen as the autocorrelation function evaluated at delay 0. See that? This is the autocorrelation function of the random process, at least wise and stationary real, and evaluated at 0. So let's again visualize this one. So here is your autocorrelation function of delay tau. And here is R sub xx0, right? Why it is always non-negative, by the way? Why it is always non-negative? Because this is what? This is that one, when it is at least wise and stationary. See that? Due to this definition, R sub xx0 is expectation of x of t times x of t. X of t times x of t is x squared t, which cannot be negative, right? So this is non-negative. And also, if it is 0, the random process is 0. And we do not assume that. So it must be positive, which is not 0. So that's why I put mark here, y-intercept here in the positive real. Got it? And now this can serve, this inequality means that this value can serve as an upper bound of the absolute value of the autocorrelation function. But what we are going to draw is not the absolute value, but the function itself. So we choose negative r sub xx sub 0 for the lower bound. Then what does this inequality mean? The autocorrelation function lives inside this band, right? And also, it cannot exceed this value. So, by the way, since this value is realized, probably something like this, right? And also, according to this necessary condition, it must be even symmetrical. Got it? And we've seen already one of the very strange autocorrelation function. That first example I've shown you here. What was the autocorrelation function? Cosine function, right? So in that very special example, the autocorrelation function is the cosine function. So not only at tau equals 0, but also at countably infinite tau, the autocorrelation function can touch this upper and lower bound in that special case of mean ergodic random process. However, as you will see, in general, usually this maximum is achieved in most of the cases. This maximum is achieved only when tau equals 0. In most of the practical examples, not that special cosine thing. Got it? So you always, I recommend you always need to remember that example, that strange thing, as a possible counter example of your some true-false problem, for example. Got it? However, that example is too special, however important. Got it? Anyway, so first thing is that it's even symmetrical, and second thing is that the autocorrelation function must be bounded by the function value evaluated at 0. And here goes some other statements. If X has periodic component, this property says that, then autocorrelation function will have a periodic component with the same period. It seems it makes sense, right? Suppose this is the time axis, and each sample path has periodic component. For example, cosine term, constant cosine term. Then, due to this periodicity of cosine term, you will see something is periodic, even though you average over large time, or even though you average using the ensemble average. And that is exactly what this special example shows, right? Each sample path is a cosine function, and autocorrelation function is also cosine function with the same period, right? See that each sample path has frequency f0, and the autocorrelation function has frequency f0, right? And so this special case, special example corresponds to this statement. It has a periodic component, and autocorrelation function has periodic component. Got it? And now let's see another property. The real valued at least y and stationary random process. In this case, we only consider at least y and stationary for a while because that is simple. And also that is meaningful because we are going to anyway use kind of assume ergodicity. And in order for something to be ergodic, at least mean or autocorrelation, at least it requires to be y and stationary. Otherwise, the mean function is a time function. Then how can it be, in most of the cases, be ergodic? Anyway, so let's see if the ensemble mean is 0 for t and no periodic component. This condition excludes our special example, right? Because our special example, the above example, even though it has 0 ensemble mean, right? Due to the random theta uniform, this is 0, you can easily show. However, it has periodic component. So let's ignore this cosine function. In that case, what does this property says? And ergodic, then interestingly, autocorrelation function. If you increase the delay, then it goes to 0. By the way, what is the physical meaning of this one? In order to know that, let's go back to our definition. So it's t plus tau and x of t. And if you still do not feel anything, put a number as you have been doing in every mathematics exam. So let's put something, okay. T equals 0 and tau equals million years, for example. Then what does that mean? This is million years, and this is current time, right? So you have some Cosby index today, right now, and Cosby index in million years. Probably human being is extinct by that time. But anyway, let's hope our Cosby, the stock market, flourish by that time. And what do you guess? They are, if 0 mean, they are likely to be uncorrelated. So it makes sense. What does this mean? Whenever you see something tends to infinity, don't take it literally as written here, as purely mathematical. As an engineer, whenever you see this, you interpret that one as what? For sufficiently large something, which means that here, for sufficiently large time difference, the 0 mean random process sampled at very large time instance, separated far away, they are what? Equal 0 means that for sufficiently large, approximately 0 or close to 0. So uncorrelated. So this means that asymptotic uncorrelatedness. Asymptotic means in Korean 점근적으로 asymptotic uncorrelatedness. But be careful. Our special example says that what? This is not true because this condition is violated. So we still have a special example. Be careful, right? Stark and Wu's textbook mainly talked about this property. And actually, they assumed no periodic component. If there is periodic component, this is not true, okay? Now, let's see a non-zero mean case. Here, we have had the 0 mean case. Here, we have non-zero mean case. So suppose this mean, as you see, this mean is, even though it's constant, is non-zero. In that case, we can subtract this non-zero mean and define a new random process, n of t. That is now having 0 mean, right? If you take the expectation of n of t, it is expectation of x of t, which is same as x bar. So you have 0. And we still assume that x is at least y and stationary. And you can easily show that n of t is now Zero mean at least wise and stationary. Zero mean at least wise and stationary random process. And also again, we assume no periodic component. Because this periodic component makes everything very complicated. And every case, if random process has periodic component, it is very special. The problem is this. Suppose you build a machine learning model or neural network model to earn automatically some 100,000 Korean won every day from stock market. So you have built some program. And you, for example, use this kind of property, that kind of property to train your machine learning model or neural network based on the previous stock market history, right? That is so-called backtest, okay? You have previous history of Korean and Kospi, New York Stock Exchange stock market history, and you have many, many random processes, and you take the chunk and then you train your system. That is usually happens. But there is a serious problem if you use this kind of assumption. Why? Because of the periodicity of our human life. Due to the revolution, not the rotation, revolution of Earth around the sun. We have 4 seasons, and many of our stock market indices depends on the seasons. For example, suppose you have Delmont Company in the US stock market that sells a lot of orange juice. What do you guess? That will not sell well in winters, right? And it will sell very well, and it may have a very high profit during summer because a lot of sunlight will produce very low-cost orange juice, but they will not reduce the price compared to the winter, which means that if you sell a lot of orange juice, drinking orange juice, kids drinking orange juice, playing soccer and baseball during summer and winter, their profit will go up. And usually our stockholders love those stocks that generates profits during a short period and see, oh, Delmont has, okay, second quarter, very high profit. Let me invest. In that case, the price will go up. And eventually in winter, it will drop, right? So we have seasonal periodicity that may seriously damage this kind of assumption because of periodicity. So we have to take into the periodicity always, but it's very difficult. For example, suppose we consider investing POSCO that sells steel products, right? Do you believe that has some seasonal, 계절적인 in Korean, seasonal dependence, periodicity? No or yes? What do you guess? No? Yes? It's very difficult because we do not know how they buy their raw materials from many countries. For example, their coal may be imported from Chile that has in the southern hemisphere. And in winter or in winter in Korea, there may be many, many low-cost product, low-cost coal which can be imported. And POSCO may have some other route importing coal from, for example, China. And in summer and that season, they may low cost. In that case, seasonal dependence may be smoothened, right? But nobody knows. We don't have that detailed information. Given that, we may assume this kind of thing, and we may be seriously ruined. So be careful. So whenever we think about some neural net or machine learning model that automatically earns some money from stock market. That may be one of our dreams. And that dream may be apparently realized for a short period. For example, Hyosung and I, for example, build some program. And we started to invest in Kospi, for example, Codex 200 and Codex Inverse. And we watch for 2 months. Hey, every day, based on just 10 to the 8 Korean won, every day we earn 300,000 Korean won. And we compute that and project what happens. And we found that, hey, we are much better than Leo Dalio, who is known as a kind of guru in stock market. Hey, we will be very rich soon. But suddenly in 2 months, our market could plunge. And even though we programmed very cleverly, because some of you already know that Kospi 200 follows the Kospi index most of the time, and inverse kind of exactly, not exactly, but mostly move opposite. So what happens is that if we theoretically cleverly program, when the stock market increases, we may invest on Codex 200. If it goes down, or we believe it goes down, we move our all money to Codex inverse. In that case, Kospi goes down, but our profit goes up. So theoretically, if we can switch very cleverly, we can always earn money, theoretically. But it may not be true. And that is very strange thing, but our assumption, if assumption is wrong, then we may not switch cleverly. We predict wrong, incorrectly. So according all the previous data and our assumption, ergodicity or something, hey, I'm sure that from tomorrow and for 2 weeks, the Kospi will plunge. Okay, so let me make a decision to move all my money from Codex 200 to Codex inverse. I'm sure I will earn money. But according to my calculation, that probability was very high, almost 1. However, the market could move opposite, exact opposite. In that case, I may lose a lot of money, which I previously collected. Nobody knows. So that is the difficulty. So automatic money generator from stock market may be very difficult. And it could mislead you. For example, as I told you, for 2 months, you may get some money. And for the next 1 month, you may lose all the money. It's very similar to the situation when you go to Las Vegas and play the roulette. Actually, this winter, early in January, I went to Las Vegas with undergraduate students. And in my first time in my life, I played the roulette. I earned, according to my calculation, large money. That was not large because I started from around 100,000 Korean won, 10만 원. And it moved to 200,000 Korean won just in 2 days. I got a lot of impression. Hey, it seems I'm a second Leo Dalio. And eventually I lost. So I lost more than 100,000 Korean won. Just in 20 minutes. Can you believe that? It's like goes up, and suddenly plunge. My mistake. Even though I'm teaching probability and random processes here and for a long time, I made a stupid belief. Anyway, so be careful. Okay, periodic component may completely ruin your plan. Never forget. Anyway, but if there is no periodic component, so what can you do? You may do this. you may have a random process y of t that has some periodic component, some a cosine 2 pi f0 t dot theta. And suppose this term makes y of t having a periodic component. In that case, one of the trick is so-called pre-processing in machine learning and other statistical signal processing, so-called in Korean 전처리. So what you do is that you subtract that one. And then this y of t can be approximately y-stand stationary and zero mean. Now you separate periodic component from your assumption. Then you can apply this, you can assume that kind of properties, right? So many people pre-process their data by subtracting some linearly increasing term, some quadratically increasing, or so what they do is that they watch the scatter plot. And they really observe whether there is some non-y-stand stationary component, and they try to subtract that one. So they have some periodic or nonlinear process plus y-stand stationary random process. Then for that part of y-stand stationary random process, you may use this kind of assumptions to make a prediction. Got it? Anyway, be careful. Here, so what does this mean? Take a look at the difference. They have the same left-hand side, but right-hand side is different because we assumed zero mean and non-zero mean. So let me draw the two cases. So it's like in the upper case, you have something like this, okay? So as tau becomes large, autocorrelation converges to zero. For the lower case, you have what? You have something like this. You have here x bar squared, and then you have something. Got it? So this is possible. But if you subtract the mean, then the random process may have that kind of autocorrelation function. So here goes an example from the Peebles book. Suppose your autocorrelation function is 25 plus 4 over 1 plus 6 tau squared. Now, can you picture this function's graph in your mind? So you have 25, and what is this? It's a kind of bell-like curve, but it's not, we call bell-shaped. But anyway, let me draw this. So at 0, we have 29, and sorry, something like this, right? So as tau tends to infinity, it converges to 25, like this. Got it? And we assume that x is a stationary ergodic process with no periodic component. And you ask mean and variance to find the mean and variance of the random process. Here, one very important thing you remember, because here it is a squared mean. That means that even though the left-hand side limit is 25, we can never know whether the mean function is 5 or -5, right? Because it just says that x bar squared is 25. So the Peebles book says that we don't know the mean. Mean may be +5 or -5. But there is actually a way to check that. What do? We just observe the sample path. Because in most of the cases, +5 and -5 could be determined from the sample path. We see, and hey, definitely the mean is 5. Definitely the mean is -5. We may be able to decide. So the lessons from statistics or probability is that you always go back to the scatter plot or raw data, the first-hand data. And that provides you a lot of information. Do not just rely on some Excel file that shows only numbers. You plot, okay? And I see Youngchang smiles. Anyway, and the variance. Variance is what? By definition, the variance is the ensemble average of x squared minus squared mean. And we know this value because this is simply the autocorrelation evaluated at 0, which is 29. So we have 29 minus we have 25. So the variance is 4. Got it? What does this mean? The standard deviation is 2, right? And we know that in many cases, if we assume Gaussianity or something, or even we may apply Markov or Chebyshev inequality and see that our realized sample may not deviate much from the mean. So from the mean, usually plus minus 2 sigma is enough to say whether mean is there or not. And as you see, mean could be +5 or -5. 2 times standard deviation is 4, which means really means that if you observe the realized sample path, you may determine whether the mean value is 5 or -5 in most of the cases. Of course, you may make an error. That is always the problem of statistical inference. If the problem is not a singular, strange, extreme problem, 특이점을 가진 문제, unless the problem is singular, you always have non-zero probability to make a mistake. Be careful. Anyway. Okay, let's see another example. Here, we assume that a Y-sense stationary, that is, of course, at least Y-sense stationary random process real valued, has autocorrelation function like this. So again, let's plot that one. What is that? That is kind of follows the exponential function on the right and left. And according to our naming, the shape is proportional to the Laplacian random variables PDF. So we have something like this, right? Sorry, 0 tau. The question is determine the autocorrelation function of y, that is x of t times cosine omega 0 t plus some theta. And we may define this as 2 pi f0 because we are mostly communication majored people and we love hertz than radian per second. Now, since we are asked to compute the autocorrelation function of y, let's start from the definition. And I'm sorry for the use, but I'd rather change this to that one. But actually, they are the same because it's assumed the x of t and y of t are assumed to be real, right? Anyway, they are the same in this problem. Now we plug in the definition. So it's kind of step-by-step procedure as we have been doing from our elementary school math. So we plug in and we use cosine times cosine equals blah, blah, blah. And we also use the this given condition. Interestingly, the autocorrelation function of the random process y of t, which is a kind of modulated version of cosine function by x of t. So if I plot, then it's like this. You have y-sense stationary random process of t, and you multiply cosine 2 pi f0 t plus some random variables theta to have y of t, right? So it's simple what? amplitude modulation with random phase. Got it? And as you see here, this is a function only of tau. That means there exists a single variable function which serves as the autocorrelation function of the random process y. What does that mean? The autocorrelation function of y is only dependent on the time difference. And what do we want to find in addition to this? Probably we want to find, hey, what is the, by the way, then, mean of y? And which is very simple because if we plug in then what? If we assume independence, which is assumed in the textbook, even though I didn't state, then what do we have? If x does not have periodic component, what do you guess? Expected value of x. See that if tau tends to infinity, it converges to 0. Implies that x bar squared equals 0. So y bar is 0. Then we have 0 mean of y of t and autocorrelation function of y dependent only of tau. What does that mean? In this problem, x of t is y and stationary, and y of t is 0 mean y and stationary random process. Got it? So we can use the previous properties to derive something that is very interesting. Okay, that's all for the day. And you may have found that I made a very slow progress, but I believe you have a very clear understanding of the material. Next time, we are going to extend these properties for autocorrelation to cross-correlation. And also see some other properties very quickly, hopefully. And then we cover the material for the discrete time, which is very simple, just straightforward. And then we are going to move to the measurement of correlation functions, which is really related to the ergodicity. In order to, for example, train our neural net for the stock market auto robot investor, we may need to extract the information, autocorrelation information from the history. That part is related to this section. That's all for the day.